Hey everyone, welcome to the inaugural video of Miss Blue's Calculus Clues. This is yours truly, Miss Blue, coming at you today with the first ever mini video lecture that I'm going to be giving you guys on a regular basis while we're doing some remote learning. And our topic today is going to be general solutions to differential equations. And when we talk about general solutions to differential equations, it's really a fancy pants way of talking about indefinite integrals. It's another term that we use that essentially is the same thing as those indefinite integrals that you already know and love. So the last couple of days before we went to remote learning, we spent a lot of time, or at least a class and a half, if that's a lot of time, talking about slope fields. And slope fields were a way that we could create a visual representation of these solutions. So we knew that a function had a particular derivative, but we didn't know what the original function necessarily was. But we knew and used the definition of the derivative as the rate of change or the slope of the function to create these visual representations that kind of helped us to see what the antiderivatives might be. So today we're going to roll up our sleeves and talk a little bit more about how we can find these general solutions in a more algebraic way. So let's start with two really basic ones that you guys are going to be able to fly right through because you understand the fundamental theorem and the whole concept that integrals and derivatives are almost like inverse operations of each other and they undo each other. So if I had the differential equation dy dx equals x, we would be able to find a general solution to this differential equation by saying, what would the antiderivative be? And the antiderivative of x would be 1/2 x squared. Now, because we want to make sure our solution encompasses all the possible solutions, we're going to make sure that we add a constant that will represent here using the letter C. So if our differential equation is dy dx equals x, then our general solution to the differential equation is y equals 1/2 x squared plus c. Likewise, if we had a differential equation like this one, we could again rely on our knowledge of derivatives and the fundamental theorem to determine that the antiderivative or the general solution to this differential equation would be y equals negative cosine x plus a constant c. By making sure we're adding that constant c, we are representing every single possible antiderivative of that particular differential equation. So now let's talk about when we can't just simply work backwards. So let's say we have a slightly more complex differential equation. Electronically, but I'm still making the same obnoxious noises. Let's consider this differential equation. dy dx equals, let's say, that's not the one I wanted to do first. Negative x over y. I believe this was one of the ones that we graphed a slope field of a couple of days ago. So this is a nice differential equation, but as I'm looking at this, there's no way, given the tools that I have in my toolbox right now, that I can take this one and say, oh, I know exactly what the antiderivative of this function is. And so I need another strategy. So we're going to do something that's called separation of variables. And separation of variables tells you exactly what you're supposed to do. We're going to algebraically separate the x terms and the y terms that are given here in our differential equation. And then we're going to integrate each side. So I'm going to take each side here and I'm going to multiply it by y. And I'm going to take each side of my equation here and I'm also going to multiply by dx. So when I take each side and multiply it by y, my differential equation will look like y times dy dx equals negative x. And if I take each side then and multiply it by dx, then my differential equation is now going to look like y dy equals negative x dx. So this is what we mean when we say that we're going to solve this differential equation using a separation of variables. So I have separated my y terms on one side and my x terms on the other side. So now what I'm going to do is I'm going to integrate each side. So I'm going to integrate the left side and I'm going to integrate the right side. So I need to now look at each piece separately. If I integrate y dy, the antiderivative of this integrand would be 1/2 y squared. And if I were to integrate the right side of this equation, I would get negative 1/2 x squared. Now, because this is a general solution to a differential equation, I do need to add a c. Now, I could add a c on the left-hand side and a c on the right-hand side and have like a c1 and a c2, and then I could combine their powers and subtract them from one another and move them to one side of the equation and call it c3. That becomes so algebraically cumbersome. So what I'm going to choose to do instead is I'm just going to put one constant on the side of the equation that has my variable for x. And this accounts for the constants that are being added on both sides here. So now what I have is an equation that looks a lot like an equation for a circle. So if I add 1/2 x squared to each side, I have 1/2 x squared plus 1/2 y squared equals some constant c. And I end up with a circle with a radius of 2c that is centered at the origin. And 2c, you might ask, comes from taking each side of the equation and multiplying it by 2, so that this is in a more kind of traditional form, more, I don't know what the word is, for a more standard form, I should say, for a equation of a circle. So I multiply each side by 2, and I get x squared plus y squared equals 2c. Well, it's still a constant. It's just 2 times my original constant. So I'm just going to leave it still as plain old c. This is the general solution to that particular differential equation. And if you look back at your homework for a couple of days ago, when you created a differential equation, a slope field rather, for this particular differential equation, you should have started to see a bunch of concentric circles. Circles that were all centered at the origin, but had varying radii. And that's what we just showed here algebraically. So it's a nice look for us here. So that's my first example for you of what these might look like when we're doing a separation of variables. So let's look at one more example that requires separation of variables. So let's consider this last differential equation. And this one's particularly weird because there's no x in sight. Let's consider the differential equation dy dx equals y. Now, just like in example 3, we realize here there's no way that we can simply look backwards and work backwards here to find the antiderivative and the general solution. So we're going to separate the variables. So what I'm going to do, I'm going to begin by taking each side and I'm going to multiply it by 1 over y. When I do that, I have 1 over y dy dx equals 1. And then I'm going to take each side of my equation and I'm going to multiply it by dx. So when I do that, I have 1 over y dy on the left and I have 1 dx over here on the right. And so what I'm going to be able to do after that is, now that I've separated my variables, I have exclusively variables in terms of y here on the left-hand side and exclusively variables in terms of x on the right-hand side. I'm going to integrate both sides. So I'm going to consider the right side first. That one's simpler, so we'll tackle that part first. The antiderivative of 1 dx is just x. Now, the antiderivative of 1 over y dy requires a little bit more thought. You're going to want to take the b and do the power rule backwards. And then you're going to realize, oh snap, I'd end up with a power of 0. And that's not going to work out, because if I take y to the negative 1 and add 1 to its power to find its antiderivative, I'll get y to the 0, which is 1. So I must be looking for a more unusual sort of antiderivative. The antiderivative that you are looking for is the natural logarithm of y. So this would be the natural logarithm of y. Now we need to be really careful when we take the antiderivative of a natural logarithm. There are 2 ways that we can handle this. We cannot take the natural logarithm of a number that is 0 or negative. And so we need to account for that in some way when we take the antiderivative. There are 2 ways that you can think about doing that. You can put a restriction on the solution once you have found out that the antiderivative is the natural logarithm of y. That's the way I like to do it. I'll say y must be greater than 0. The other way to handle it is to say that we are taking the natural logarithm of the absolute value of y. So that's kind of, if I do a second method over here, I could also say my antiderivative would look like that. Most of the time on the multiple choice questions on the AP exam, if you're finding an antiderivative, you're going to see that absolute value. It's less cumbersome. But a lot of times within the context of the problem, it's easier to, or just as simple to denote, we are restricting our values of y to be those that are greater than 0. So now, again, as in the last example, I am going to account for all the constants on the left and right-hand sides of this equation with a single constant added to the right. Now, if we wanted to, we could then take this logarithmic function and rewrite it using exponential definitions so that we could write it in a form that looks like y equals. So the natural logarithm of y equals x plus c is another way of saying e raised to the x plus c equals y, where y has to be greater than 0. Likewise, I could take my solution over here and write it in a similar way, that e raised to the x plus c equals the absolute value of y. Now we know that e raised to any power is going to yield a positive solution, but it's just an important thing to note here that when we take that antiderivative, we need to be clear that that the quantity that we are taking the natural logarithm of is in fact positive. So I hope this helps. I'm going to be giving you guys some extra exercises to work on where you'll get an opportunity to practice some of this separation of variables business. Keep asking questions, keep communicating with me, hang in there, and I look forward to hearing from you guys again in the near future. Take care.